Okay, let's unpack this. We spend so much time learning how C++ programs manipulate data. We're talking variables, objects, vectors,
Right.
all living in that, fast, volatile world of memory. The stack, the heap.
Huh.
We do the calculations, we solve the problem, and then the program ends.
And all that valuable data just vanishes. Gone.
Oof.
It only had a temporary existence. Our deep dive today is, well, it's about mastering the essential protocol for achieving data persistence.
Oh,
We're moving information across the border from that temporary memory space to the stable, permanent safety of secondary storage.
that's our mission then, to distill the core concepts of C++ file input-output. We're focusing on how we turn those fleeting calculations into reusable permanent knowledge that can, survive a reboot.
And the fundamental concept here is the stream.
The stream.
Exactly. A stream is an abstract object that represents the flow of data. Now, everyone listening is already familiar with standard I/O streams like SYN and COUT, which use the I/O stream header.
Right, for keyboard input and screen output.
Those streams manage data flow from the keyboard or to the monitor.
So if the stack and heap are temporary residents, standard I/O streams are just, what, temporary phone lines for a real-time chat? They don't touch the hard drive?
Precisely. File streams, however, are the mechanism we use when we want to communicate with persistent storage. Your hard disk, an SSD, a USB drive, that's the gateway to permanent storage.
And the key to that gateway.
The only way to manage that flow in C++ is through the upstream header file.
Fstream. Okay, so that's the key. But if it's all just moving data, why do we need two totally separate stream objects? Why not just have one generic file object and flag it for input or output?
That's a great question. And it really gets to the heart of resource management and safety.
Okay.
While they are conceptually similar, the required protocols for input and output are fundamentally different, especially when you think about error handling and security.
How so?
Well, an input stream, an if stream, has to guarantee that the file exists before it can do anything.
Right, or there's nothing to read.
Whereas an output stream, an off stream, has to guarantee it has write access and, critically, decide whether to destroy existing data. Having two distinct objects enforces a really strict separation of duties.
That makes sense. It's about managing the unique risks on either side of that border crossing.
Exactly.
Let's start on the input side then. Reading data into the program, this needs the if stream object. What's the protocol for bringing that persistent data home?
We can break the process into three critical stages. This is the essential file I/O protocol.
3 stages.
Stage 1, acquisition and verification. You create the if stream object, and you'll often pass the file path right into the constructor to open it.
Simple enough.
But this is where the first major risk appears. Unlike creating a new file, opening an existing file for reading is a massive failure point if that file doesn't exist.
Ah, so you get an immediate program halting runtime error.
You got it.
So you have to build in robustness from line 1. If we're trying to read that sample file from the sources demus filio input file.txt-elegant, we absolutely must verify it exists right after we try to open it.
Correct. Good programmers will immediately check the stream object itself. You can treat it like a Boolean to make sure the open actually succeeded before moving on.
And if it failed?
You handle the error, exit gracefully, prompt the user, whatever you need to do, don't just let it crash.
Okay, so verification passes. We have an open file. Stage 2 is extracting and parsing, right?
Yes.
Now, everyone knows the operator, but how is reading from a file, from a text stream, different from just reading from the keyboard with SYN?
The mechanics are actually the same. The extraction operator still stops at whitespace or at a type mismatch.
Okay.
But the context is totally different. With a file, you're usually dealing with a variable amount of data, not just one quick prompt. So the big difference is the loop structure you need to handle the end of the file, or EOF.
EOF, right.
You have to rely on the stream object itself to tell you, hey, I've reached the end, usually inside a while loop, processing data item by item until the whole file is parsed.
And that parsing is where the real work happens. If you're reading, say, a bunch of coordinates, you have to be really careful the input types match what's in the file.
Yes, and if you're dealing with text, with spaces, you'll use getLine. But regardless of how you do it, we arrive at the final and often overlooked stage, release.
Stage 3, close the file. Why is calling a simple close method so vital? It seems like the program ending would handle it.
It's vital for good housekeeping And resource release. When your program opens a file, the OS allocates resources and often puts a lock on that file.
A lock.
Yeah, to prevent other programs from changing it while you're reading it. If you don't explicitly call close,
Yeah.
that resource stays tied up until the program exits.
Which might not be a big deal for a tiny program.
Right, but if you're running a server or some complex application, those open file handles can add up and cause serious system instability. It's like a library book. If you don't check it back in, the library still thinks it's out.
That's a clear analogy. Okay, so we've moved data safely in. Let's flip it. Let's talk output. Writing data from memory to permanent storage with offstream.
Right, so we transition from reading safely to writing securely. The protocol is the same 3 steps, but the risks are, well, they're inverted.
So stage 1 for output. Create or open the file. This is where we need to put up a big warning sign for every learner, isn't it?
This is a high-stakes moment. This is where new programmers can cause catastrophic data loss. If you initialize an off-stream object and the file already exists, the default behavior of the stream is to truncate the file.
Meaning?
It instantly deletes all existing contents. It prepares a fresh 0-byte file for your new output.
You are wiping the slate clean.
Completely.
Without so much as a pop-up saying, "Are you sure?"
Exactly. If you're not careful, that one line of code just erased all of your previously saved work.
Wow. Okay, so how do you avoid that?
The only way to bypass that default destructive behavior is to explicitly open the file in append mode. You use an iOS flag when you open it.
A crucial defense mechanism.
It is. In industry, it's also common to write to a temporary file first. Then, only after the write is successful, you rename the temp file to overwrite the original.
That's clever. So if the program crashes mid-save...
You haven't corrupted your original file. It's great for error mitigation.
So once the file's open and we've decided to overwrite or append, stage 2 is writing the data.
And this is the easy part. We use the output insertion operator, exactly like we do for count and standard output. The data just flows from your variables into the file buffer.
Which leads us right to stage 3, mandatory release. Is closing an output stream even more critical than closing an input stream?
It is, for a different reason. Input files are read, but output files are often written to buffers first.
Buffers.
Yeah, the operating system tries to be efficient. It holds the data in a temporary memory buffer and only periodically flushes it to the physical disk.
So it saves it up and writes in chunks.
Exactly. But if your program terminates unexpectedly, or if you just forget to call close, there's a real chance the last few lines of data you wrote are still stuck in that buffer.
And they never physically make it to the hard drive.
Never. The close method forces that final buffer flush. It guarantees persistence.
So if my program runs fine, but the last couple of customer records are missing from the save file, forgetting close is the prime suspect.
Highly likely. It's that final handshake that guarantees data integrity.
Okay, now that we have the mechanics down, let's connect this to real-world utility. How do these streams actually work together?
They often work in concert. A perfect basic example is file copying.
Okay.
You initialize an if stream for your source file and an auth stream for your destination simultaneously. You just read chunks of data from the input and immediately write them to the output until you hit the end of the input file.
It's the ultimate border crossing exercise. Data in, data out.
Exactly.
And when we write, we don't just want a messy string of numbers. We need the data to be clean, structured, readable.
And that's where consistency pays off. The IO-manip library manipulators, which we all use to format numbers for the console,
Set precision?
all of them, they apply identically to file output. So whether you're using fixed or set precision for floats or set and set fill to make columns line up perfectly, those tools create a structured, standardized output file.
So I can create clean data logs or even CSV files without learning a whole new syntax for file formatting. That's a huge time saver.
It is. It transforms a raw data dump into a reusable data asset.
Let's look at the applications from the source materials. What about the geometry calculations, finding distance, area, perimeter? Why does file I/O suddenly become necessary there?
Because a useful geometry program shouldn't make you manually type in 10 sets of x, y coordinates every single time you run it. That's not useful.
Right, that's tedious.
The program's value comes from its ability to just ask for a file name, say pointdata.txt. Uses ifstream to pull in all those coordinates, radii, whatever, and then stores that data efficiently, maybe in a std.vector points.
Which means we're solving the parsing challenge. We're not just grabbing one number. We're extracting multiple data types on each line and building complex objects in memory.
Precisely. The persistence lets us separate the data management task from the calculation task.
And once the calculation's
An
done,
app stream takes the result and saves it to a designated output file. The persistence loop is complete, the results are validated, and more importantly, secured.
but the ultimate application, the one that really shows the difference between a simple script and a foundational application, has to be the airline reservation system.
This is where I/O moves from being a utility to an absolute necessity.
It's not just a one-off calculation.
Not at all. This system is menu-driven, maybe managing a plane with 10 rows, 2 seats per row.
Yeah.
If you think about it from a memory perspective, every time a seat is booked or a price is updated, that change happens in volatile RAM.
So if the user closes the program, every single booking, every price change, it all reverts back to how it was when the program started.
The entire business model fails instantly. The integrity of the business depends entirely on file I/O. At startup, the system must use ifstream to load the current seat map and pricing from a persistent file. This is the load state operation.
So we use our parsing skills to rebuild all our data structures, our vectors, our matrices in memory exactly as they were when the program last shut down.
Yes. And crucially, throughout the runtime, every successful booking or price change has to trigger a safe state operation.
Okay.
This means using OStream to rewrite the entire current updated data structure back to the file. It's a constant commitment to persistence.
Without that loop load on startup, save on modification.
It's not an application, it's just a demo.
The complexity there, managing that state, making sure the file isn't corrupted, preventing accidental truncation, that makes the stakes incredibly clear.
That's the difference. A simple script solves a problem once and then forgets. A real-world application, like a reservation system, manages a living, persistent data model. It unlocks knowledge that builds on itself.
This has been a true deep dive into persistence. Let's recap the synthesis here. File streams are the essential link to permanent storage, and you need that fstream header.
We covered the 3 stages for input with ifstream. Acquisition and verify that file exists. Extraction, where you manage EOF, and release, which means you must call close.
And for output with fstream, creation, where you have to be aware of that catastrophic truncation, writing, where you use IO for structure and mandatory release to flush those buffers and secure the data.
It's all about control, safety, and durability. Mastering that flow is foundational.
So if we look at the bigger picture, our sources mention that most competitive programming, like on sites such as Codis, focuses almost exclusively on standard I/O, keyboard in, screen out. They're for solving immediate singular puzzles.
Which brings up a really important question for you, the learner. We've spent this time mastering the complexity of file I/O handling truncation, designing robust load-safe state operations for something like that airline system. If standard I/O is about solving that single, isolated problem at a competition, what does the ability to permanently save and recall data, to maintain a complete operational state over time, reveal about the ultimate purpose of programming? What kind of persistent systems, products, and knowledge can you create when your data structures never have to die and the results from today become the foundation for whatever you build tomorrow?